Welcome to Math 201, the lesson for section 3.6, derivatives of inverse functions. Let's start, as we always start in these chapter 3 lessons. We're going to list all the derivative rules and shortcuts we have learned thus far. So we have the power rule. The derivative of x to the n is nx to the n minus 1. We have the exponential derivative rule. So the derivative of a to the x is a to the x times the ln of a. And we have a special case of that one for e to the x, because the derivative of e to the x will follow the a to the x rule. So it would be e to the x times the ln of e, but the ln of e is just 1. All right, we also now have some trig derivatives. We have the derivative of sine is cosine. We know that the derivative of cosine is negative sine. We know that the derivative of tangent is secant squared. We know that the derivative of cotangent is negative cosecant squared. And we know the derivative of secant is secant tangent. And we know that the derivative of cosecant is negative cosecant cotangent. So we discovered all those trig ones in our previous lesson. We also have some more general rules that we have been learning. So I think I'll do those in a different color. So more general rules that aren't specific functions. We have the product rule. The derivative of f times g is f prime g plus f g prime. The derivative of a quotient, f over g, is f prime g minus f g prime over g squared. I know that the derivative of a sum or a difference, f plus or minus g, is f prime plus or minus g prime. And I know that the derivative of a constant times a function is just the constant times the derivative of the function. Ooh, okay, we got them all. We're starting to not be able to fit these all on one slide, but oh, I have one more. I have the chain rule. I also have the chain rule that I learned 2 lessons ago. F of g of x is f prime of the stuff times the derivative of the stuff. Okay, let's go back and think about the concept of inverse functions. So this is another prerequisite concept that you should have seen before this course. Inverse functions are functions that, quote, undo each other. So consider 2 function machines running back to back. So if I have a function machine G, okay, and then another function machine that takes the output from G and runs it through the F machine. So I put something into G, we turn the crank, G does something to our input and it outputs something, okay? It outputs, we'll call it G of X, okay? A Y value. So we take that X, we put it into G and it makes a Y. If you take that Y and put it into F, if F and G are inverses that undo each other, then what I get out of F is what I originally put in. Okay, so I put an X into the G machine, it changes it into a Y. You take that Y and run it through the F machine, and F just undoes whatever G did and gives you the original X back. So that means that F of G of X is X. And you can run the machines in either order too. We can say g of f of x will also give you x, okay? Because g and f undo each other. The order doesn't matter. And then typically we rename one of the functions um, to represent the fact that it's inverse. So let's rename g f with this little -1. So instead of calling it g, we're going to call it f inverse, the function that undoes f. So formally, in mathematical notation, we say that two functions are inverses if their composition is always x. So f of g of x is x and g of f of x is x. They undo each other. Two machines running back to back. If you plug an x into the g machine and then take the result and put it into f, you get the x back, and vice versa. And we typically rename g of x f inverse of x. Some examples of pairs of inverses, functions that undo each other, could be f of x equals 5x, and f inverse of x could be x over 5. Okay, so if you multiply by 5, one function multiplies by 5, the other function divides by 5, they undo each other. Another sort of simple one could be x plus 3, and its inverse would be x minus 3. One function takes an input and adds 3, and the other function takes an input and subtracts 3. So some other examples might be x cubed, and what undoes cubing? Cube rooting. So this would be the cube root of x. And then some more advanced examples might be tangent x and arctan x, which is also known as inverse tan x. And exponentials, the inverse of e to the x, the exponential e to the x, would be the log function ln x, the natural log. Let's just pick one of our examples and compose them. Let's look at f of x equals 5x and f inverse of x equals x over 5. So f of f inverse of x. Okay, that would be f of, so instead of f inverse of x, I'm going to replace f inverse of x with its formula, x over 5. Okay, f of x over 5, that means because I've replaced this x in the parentheses with an x over 5, that means replace every x in the formula with an x over 5. So this is 5 times x over 5, which is x. Okay, so when I compose them, I do get x. And the other order should work as well. If I do f inverse of f of x, this would be f inverse of f of x is 5x. So now I'm going to plug a 5x into the formula for f inverse. So I have 5x over 5, which is x. So those are, in fact, inverse functions. When you compose them, you get x. Okay, so we listed e to the x and ln x as inverse functions. So we know the following fact is true. We know that if we compose e to the x and ln x, we get x. This is the composition, e to the ln of x. We know we'll get x. Those undo each other. By taking the derivative of both sides of this equation, we could solve for the derivative of ln x. So that's what I'm going to do. I'm just going to take d dx of both sides. d dx of e to the ln of x equals d dx of x. Okay, now I'm going to apply my derivative rules. This is e to some stuff. So the chain rule says that the derivative is going to be e to the stuff times the derivative of the stuff. And the right side, d dx of x, is just 1. Okay, but e to the ln of x, we know this simplifies to just x. e to the ln of x equals x. So this says x times the derivative of ln x, which we don't know, equals 1. But now I could treat d dx of ln x like an unknown. This is the thing I would like to know what it equals. So I'm going to divide both sides of this equation by x and just get that derivative that I'd like to know by itself. Okay, so this says that d dx of the ln of x is 1 over x, and I have another derivative rule. I use the fact that e and ln are inverses, so when I compose them, I get x. Then I took the derivative of both sides, used the chain rule, and I was able to solve for the derivative of ln x. Let's use a similar technique to find the derivative of arctan x, also known as the inverse tan of x. So I'm going to start with a true fact. I'm going to start by composing two functions that undo each other, tangent and arctangent. So the tangent of the arctangent of x should give me x. And now I can take d dx of both sides, take the derivative of both sides. So the derivative of the tangent of the arctan of x equals the derivative of x. Okay, so the derivative of the tangent of the arctangent. So my inside function is arctan, my outside function is tan. This is a chain rule problem. This is the tangent of some stuff. Okay, so remember the derivative rule for tangent. We wrote it on the first slide today. The derivative of tangent of x is secant squared x. So the derivative of the tangent of some stuff is going to be secant squared of the stuff times the derivative of the stuff. Okay, so that's my left-hand side. And then the right-hand side of the equal sign is d dx of x, which is 1. Okay, so what I'm looking for is the derivative of arctan x. This is now a factor. This is now shown up in my equation. I can solve for this thing by dividing by this thing. So I'm going to divide both sides by secant squared of the arctan of x, and I get d dx of arctan x is 1 over secant squared of arctan x. Now, this is very messy. I would like to make this look nicer. I'm going to need another slide. Okay, I just copied down my previous line. The derivative of arctan x, I have now solved for it. It's 1 over the secant squared of the arctangent of x. But remember our reciprocal identities. 1 over secant is actually cosine. So this would be much cleaner to write as cosine squared of the arctan of x. Okay, so that feels like we should be done. However, I can simplify this using some right triangle trigonometry. Okay, so the cosine squared of the arctangent of x. So when you take the cosine of some stuff, the thing you're taking the cosine of is always an angle. So remember back to the unit circle. If I ask, what's the cosine of 2 pi? What's the cosine of pi over 3? What's the cosine of blah? I'm asking, what is the cosine of some angle? So arctan x is an angle, and we are going to rename it momentarily, temporarily, to make the problem look a little simpler. So we are going to say let theta stand in for arctan x. Because if I'm taking the cosine of a thing, that thing is an angle. And so I'm going to rename it theta, which is like a classic name for an angle. Okay. So I'm going to let theta be arctan x. So really, this is cosine squared theta. Okay. But if theta is arctan x, because tangent and arctangent are inverse functions, that means that the tangent of theta is x. So I'm basically taking the tangent of both sides here. The tangent of theta tangent theta. The tangent of the arctangent of x is going to give me x because they're inverses. Okay, so if theta is arctan x, then tan theta is x. And I could draw a picture. If tan theta is x, let's call that x over 1, and I'm going to draw a right triangle and put theta in it. And tangent, remember, is opposite over adjacent. So I'm going to call the opposite side x and the adjacent side 1. And that means that the hypotenuse, I could use the Pythagorean theorem, and I would have 1 squared plus x squared equals c squared. So c is x squared plus 1 radical. So cosine squared theta is going to be really cosine theta squared, right? And the cosine of theta in my diagram, in my triangle, cosine is adjacent over hypotenuse. So this is going to be 1 over the square root of x squared plus 1 squared, which is 1 over x squared plus 1. There is my derivative of arctan x. I'm just going to write out a final conclusion because that didn't come out in like a nice line. So d dx of arctan x turns out to be 1 over 1 plus x squared. And a chain rule version would be that d dx of arctan of some stuff would be 1 over 1 plus the stuff squared times the derivative of the stuff. Okay, you've reached the first activity of lesson 3.6. We're going to find the derivative of arcsine. Use the same technique we used to find the derivatives of ln and arctan to find the derivative of arcsine. So we start with an equation we know is true. We start by composing two inverse functions. We're going to take the sine of the arcsine of x, and we know that that will give us x. And then I'm going to take the derivative of both sides, d dx of the sine of the arcsine of x equals d dx of x. Okay, so this is the derivative of the sine of some stuff. So this is a chain rule problem. My outside function is sine. So the derivative of the sine of some stuff is the cosine of the stuff. So this is going to be the cosine of the arcsine of x times the derivative of the stuff, derivative of arcsine x. And that equals d dx of x, which is 1. Now I'm going to solve for d dx of arcsine x, because that's what I'm trying to find. I would like to know a formula for d dx of arcsine x. Here it shows up in my equation. I'm just going to divide this out, and I'll have a formula. d dx of arcsine x is going to end up being 1 over the cosine of the arcsine of x. And we might say we're done. That could be a formula for the arcsine of x, but I can simplify it a lot using a right triangle. So I'm going to go ahead and do that on the next slide. Okay. Remember in the previous example, when we were talking about taking the cosine of a thing, that thing you take the cosine of is always an angle, right? Like if somebody says, what's the cosine of blah, 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 what you're expecting them to say is an angle. What's the cosine of 240 degrees? What's the cosine of pi over 6? Right? Those are angles. So that means that the arcsine of x, this thing, is an angle. So let's call it theta. So let arcsine x be theta. We're going to give it a traditional angle name, theta. Okay, and if arcsine of x is theta, that means that the sine of theta is x, because arcsine and sine are inverse functions. So imagine we're taking the sine of both sides of this equation. The sine of the arcsine of x is x, and sine of theta is sine of theta. Okay, so sine of theta is x. All right, so now I'm doing 1 over the cosine of the arcsine of x. But arcsine of x is theta, so I'm going to put a theta there. So this is now 1 over the cosine of theta. And I'm going to draw a picture of a right triangle with theta in it. Theta is my angle. And I know that the sine of theta is x, and sine is opposite over hypotenuse. So this is, I'm going to put that over 1. So opposite side's x, hypotenuse is 1, which means that the missing side, the adjacent side, is going to be the square root of 1 minus x squared. We find that just using the Pythagorean theorem. And once I have that triangle, I can finish simplifying this expression 1 over cosine theta by replacing cosine theta with an expression of the triangle. Cosine theta is adjacent over hypotenuse. So this is going to be 1 over adjacent over hypotenuse. And then this is a compound fraction. We're just going to flip and multiply, and we have 1 over the square root of 1 minus x squared. That is our formula for the derivative of arcsine. You have reached the second activity for lesson 3.6. I would like you to pause the video, work through these problems, come back and watch the video to check your solutions when you are done. Okay, using all the tools we've learned to take the derivatives of functions, we are just going to do some practice. Take the derivatives of all these functions. So h of x is the ln of 2x. And I have to remember now that the derivative of ln x we calculated earlier in this lesson, we came up with 1 over x. Okay, so this is the ln of some stuff. So I'm going to have to use the chain rule to take this derivative. It's going to be 1 over the stuff, right? Because the derivative of ln x is 1 over x. So the derivative of the ln of some stuff is 1 over the stuff. And maybe I won't write stuff, I'll write 2x. 1 over the stuff times the derivative of the stuff. Okay, so that's 1 over 2x times the derivative of 2x, which is 2. My 2's cancel, and I get 1 over x. K of x is x times the sine of 2x minus 3. And this is a product. X times sine of 2x minus 3. So I'm going to do the product rule. Let's call this first function f and this second function g. So k prime of x would be f prime g plus f g prime. And f prime would be the derivative of x, which is 1, times g, and g is sine of 2x minus 3, plus f, which is just an x, times the derivative of g. So that's the sine of some stuff. G is the sine of some stuff. So I'm going to have to use the chain rule. The derivative of sine of some stuff is cosine of the stuff times the derivative of the stuff. So this is going to be the cosine of the stuff times the derivative of the stuff. And now I'll just simplify and take this last derivative and I'll be all set. Okay, so this is sine of 2x minus 3 plus the derivative of 2x minus 3 is 2. So this becomes 2x cosine 2x minus 3. E of t is the cosine of e to the t squared. So this is going to be a multiple chain rule problem because I have stuff inside of cosine. Okay, so t squared is like my innermost function, and that's being composed with e to the x, right? But then I'm taking the cosine of all of that stuff. So there's actually 3 functions being composed here. But I'm going to start with the outermost function. That's how we always start with these. just think of this as the cosine of some stuff. Doesn't matter how complicated the stuff is. Think about the outermost function first. It's the cosine of some stuff. So the derivative of cosine is negative sine. So it's going to be negative sine of the stuff, which is e to the t squared, then times the derivative of the stuff, e to the t squared. Okay, now we're gonna do a lot of copying in these triple chain rule problems. So I'm just gonna copy this factor that is already done, and I'm gonna work on taking this derivative. So first I'm just writing down negative sine of e to the t squared. That's part of the derivative I'm done with. Okay, times the derivative of e to the t squared. That is e to some stuff. The derivative of e to the x is e to the x, which means that the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the t squared is going to be e to the t squared times the derivative of t squared. Okay, exercise and copying here. Negative sine of e to the t squared times e to the t squared times the derivative of t squared is 2t, and I'm done. Okay, last problem, g of x is x squared e to the x minus x cubed over square root x. We could approach this using the quotient rule and call the numerator f and the denominator g. And as we're working through the quotient rule, when I'm taking the derivative of the numerator, I'm going to have to use the product rule because that's x squared times e to the x. But rather than having to use both rules in one problem, which you could do, you'll get the right answer. It just gets messy. I'm going to simplify this a bit before trying to take the derivative. So instead of square root of x, think of that as x to the 1/2, and I'm going to move it to the numerator and make the exponent negative. So that's x to the negative 1/2 times x squared e to the x minus x cubed. And then I'm going to distribute the x to the negative 1/2. So this becomes x to the 1.5 e to the x minus x to the 2.5. And now I am going to have to use the product rule, but only the product rule. I'm not going to have to do the product rule within the quotient rule. This is much cleaner. Okay, so g prime. See, I think I will call x to the 1.5 f and e to the x g. So when I take the derivative, I'm going to have f prime, which is 1.5 x to the 0.5. It's f prime g plus f g prime. So that is the derivative of my product, f prime g plus f g prime. And then I still have to take the derivative of the next term, minus 2.5 x to the 1.5.